We'd like to welcome you to the TAPI Engineering Division and Environmental Work Group Knowledge Share on PFAS regulatory impacts on the pulp and paper industry. Our panelists today are Dr. Gift Johnson from NCASI, Dan Curry from TRC, and Charlie Liu from Kennedy Jenks. My name is Heather Jennings, and I will be your moderator today. Before we start, we'd like to take care of some housekeeping. Oops, went a little fast there, but the meeting will be held in accordance with the TAPI's antitrust policy. TAPI's aim is to promote research and education and to arrange for the collection, dissemination, and interchange of technical concepts and information in fields of interest to its members. TAPI is not intended to and may not play any role in the competitive decisions of its members or their employees or employers, or in any way restrict competition among companies. Detailed information on TAPI's antitrust policies can be viewed at tapi.org. We'd also like to cover TAPI's commercialism guidelines. Although commerce is a driving force for our technologies, TAPI technical sessions are not a platform for commercial sales presentations. Presentations that are technical and objective enhance the credibility of the presenter and his or her organization. Restricting commercialism ultimately benefits both the presenters and the TAPI audience. Detailed information on commercialism guidelines can be viewed at tapi.org. And now I'd like to turn the time over to Scott Curry.
Hi, thanks, Heather. I'm Scott Curry, Managing Director of CQ Strategy. I've been helping Heather behind the scenes a little bit with this. TAPI's engineering division is one of the key groups that we're bringing this presentation together. The division consists of many technical professionals across multiple engineering disciplines with lots of skills, knowledge, and experience. These people focus on the application of engineering principles in the design, construction, operations, and maintenance of facilities for the manufacture of the pulp and paper related products. Next slide. And a little point about the Environmental and Sustainability Working Group. Within the engineering division, there's about seven different subgroups, either committee or working group. The Environmental and Sustainability Working Group is one such. And this group focuses on the interrelationships of operations and environment, namely air and water resources, solid waste disposal, and sustainability. And the group actively promotes and assists to set forth programs around environmental control with the goals to collect and disseminate technical information and technology updates, promote professional growth and competence in environmental issues, and enable employers to address environmental issues of the industry and facility. Thanks, Heather. And I'm going to turn this back to you.
Thank you, Scott. So today, here's the agenda that we have. Dr. Gift Johnson will be first, followed by Dan Curry, and then followed by Dr. Charlie Liu. And then we will have a Q&A open session afterwards. Please feel free to put your questions in the chat. We will address them towards the end of the in the Q&A section. And with that, I would like to introduce you to Gift. Gift, do you want to load up your presentation while I introduce you?
Sure, will do.
Okay. Dr. Gift Johnson has been a member of the NCASI team since October 2017. Prior to joining NCASI, Dr. Johnson served as a faculty member of the University of South Florida's Toxicology and Risk Assessment Program and Assistant Director of Research for the Center of Environmental and Occupational Risk Analysis and Management. Current areas of interest include bringing the best science to bear in the development of national ambient air quality standards, improving the science behind the development of human health water quality criteria, and participating in the development of emerging regulatory practices for per and polyfluorinated alkyl substances, or PFAS. And with that, we'd like to have Gift take it away.
Thank you, Heather. So, as Heather mentioned, I'm at Cassie, and Cassie's been serving the paper industry for their sustainability and environmental compliance issues for about 80 years now. Uh, I am the senior program manager for the Chemical Management Health Effects program, which has firmly placed PFAS into my purview over the last few years. And today I wanted to talk to you about basically the lessons that we've learned over the last, I don't know, 5 or 6 years of doing research, providing education, providing sampling support for paper and forest products industry, and looking at a variety of environmental matrices and things that we've learned in product testing for PFAS. Since I'm going first, I felt it was appropriate to give a little bit of a primer on what PFAS is and how it's been used in industry as well as consumer products. So in the past, PFAS has largely been phased out now in the paper industry, but it had been used previously in fast food containers, wrappers. It confers grease resistance. It's heat stable. It is highly valuable in terms of wetness resistance, grease resistance, and it's the reason why you can cook popcorn in a paper bag, because it provides also that heat resistance to the grease as you use it. If you look down at our cartoon, you can see the reason it confers these properties is because it has this long chain of fluorinated carbons that is usually attached to a functional group that allows it to be attached in various types of products. In other consumer products, Teflon is something that we typically associate with PFAS as being a non-stick type of coating. Scotchgard products, anything that confers wetness resistance, a variety of cleaning products. And in firefighting foams is actually one of the reasons why in recent years we've become more interested in PFAS as an environmental contaminant, because airports and particularly military bases were uh, using AFFF firefighting foams in practice events. When you need to put out an airplane engine that's on fire, you need a very effective firefighting, high performance firefighting foam. And they had been conducting drills and things like that to ensure that they were able to put out fires that would occur in these circumstances. And it would leached into the ground and contaminated the groundwater among many of these bases. Sampling from military bases turned up that we were getting the substantial contamination. And so it really raised the awareness for PFAS presence in all of the various products that it had been used in. And as you can see, as a result of the widespread use of PFAS in a variety of types of industries and products, you can find it in most places that you sample in the groundwater. And these levels are mostly in the single-digit parts per trillion. So, in some places they can be single-digit parts per trillion, and some places they can be double digits parts per trillion. Highly contaminated areas are going to be higher than that, but it's most commonly under 100 parts per trillion of various types of PFAS that are commonly found in the environment. So it's important to understand the other property of PFAS that makes it fairly complicated to sample for, is that if you look down at the bottom of this chart, you'll see the end chain degradation products PFAS. These are the things that actually get measured in most of the analytical methods. So PFBA, PFHXA. I think most people are mostly commonly familiar with PFOS and PFOA. Those are the two typical longer chain PFAS that were used in the 40s and 50s and 60s until they started becoming substituted for the shorter chain PFAS, such as the 6 carbons or shorter, that showed up later in more modern products. But what you can see is that the use form of these in products are large molecules that break down into various intermediates over their environmental fate and transport story. So if you are simply measuring for the 30 to 40 or so analytes that we typically look at, You're only measuring the breakdown products, and it may not give you a good sense of what's out there in a precursor form in the environment. So this can cause problems sometimes where people measure some amount of end products in the influent, and they measure more in their effluent, and they're not using any of these in their process, but it could be simply the breakdown of these precursors that are in the influent that aren't being measured that turn into the degradate chain PFAS at the end of that phase. And so you get a modest increase in those things that you can actually measure, even though you're not adding to them during a paper making process. So let's talk a little bit about the various methods that we use to evaluate PFAS in various matrices. If you can see my cursor here, which I don't think you can, but if we look down at our third block here, this US EPA method 537.1, and the fourth block, US EPA method 533. So these are drinking water methods, and for most paper facilities, this won't be relevant unless you are furnishing drinking water to your facility. In that case, it could potentially be relevant for you. But these methods depend on a very clean matrix, right? We're talking about drinking water that's been polished. So there's not a lot of interfering substances, and the method is really designed to address that type of matrix. Before we had the current US EPA draft method 1633 for wastewater, when people were trying to evaluate wastewater, they would use a modified version of 537 to try and adapt it for these, less than clean matrices that may have higher solids content, that may have different types of color, other interfering substances. And so a lot of the data that, like I showed you on that map, where they're measuring surface water concentrations, it's coming from this 537 modified method. The issue with that is that was never like an EPA sanctioned method. So laboratories essentially modified 537.1, and they all did it in a little bit differently in their approach to modifying it. So the results that you get from the older data could vary quite a lot based on the analytical approach being used to modify that method to look at waters that are not polished drinking water. So that gets us started, though, into, if we look on the other side here in our blue square, the ASTM methods that looked at aqueous matrices, that eventually the things that we learned from these other types of methods get us to the green box of US EPA draft method 1633. So this method has been approved for wastewater, solids, biosolids, tissues. It can analyze 40 of those terminal end product PFAS. And this is what is being commonly used by states in the last year or so. If you're being asked to evaluate your effluent for PFAS, this is one of the most commonly used methods to do that. And we'll talk more about that in a future slide here. I did also want to briefly, go over US EPA draft OTM 45. So this is going to be an air method looking at volatile and semi-volatile sources of PFAS. Primarily, our current regulatory interest in air sources of PFAS is how it leaves a stationary source and gets transported to then fall onto a water body, and we're interested in how it potentially contributes to the contamination of surface water. So we haven't yet seen a toxicology pathway for people being interested in inhalational exposures to PFAS, but they're still interested in measuring the air composition simply as a contributary source of contamination for surface waters and sometimes surface soils. And we also have draft method 1621. And so this is an absorbable organic fluorine. And this is going to get us into this conversation of targeted methods versus non-targeted methods. So targeted methods are where we're looking at individual types of PFAS, like PFOA, PFOS, PFHXS, and so on. The Absorbable organic fluorine attempts to take that aqueous matrix and look at a total organic fluorine component to it. So remember when we said that there's lots of precursors that could potentially exist that we don't measure in these targeted methods. The absorbable and organic fluorine and other non-targeted methods attempts to get at that fraction of it. But when we talk about similar methods being used for products, we'll talk about some of the problems that we find in interpreting that sort of total type of aggregate method. So before we mentioned that there's a substantial use of PFAS in all kinds of different products. This includes laboratory products and sampling products. So it can be very challenging actually to go out and sample for PFAS and avoid contaminating your samples with things that are just commonly found. And when we would go out and, take a dip sample and, put it in a bottle and send it off to the laboratory. So you're going to want to avoid, like blue ice, artificial ice products, anything with Teflon in it, like Teflon tape for pipes. Those can potentially leach some amount of PFAS out. There are some aluminum foils that are associated with PFAS in their processing or even in coatings. PFAS can be found in scientific equipment for bottle caps and liners. Sometimes we are concerned about sticky notes, types of balers, pump ladders, all kinds
Ya lo resolví, gracias.
I'm sorry, do I have a question? All right, I'll keep going. So you have to be concerned about how folks have sunscreens, insect repellents, how they've been washing their clothes, or what the fabric is in the clothing. Many clothes come with grease resistance, stain resistance. Those can contain PFAS. So the point is there's a wide variety of potential contaminants for PFAS sampling. So not only do you want to have a good list of PFAS-free products that you're using and use good sampling hygiene when you're sampling for PFAS, but you're also going to want to take environmental blanks when you are conducting PFAS. So taking blank samples when you're transferring samples and other types of activity during sampling, that's going to help you identify what a source of contamination is if you come up with a positive result and you're concerned that it could have come from contamination and not from your actual sample. So I wanted to talk about 1633 a little bit more simply because if your environmental manager is being asked to conduct sampling for PFAS in your effluent or your biosolids or something like that, 1633 is probably what you're being asked to use. So this is in a state where EPA has finalized it for use, but has not necessarily promulgated it. They may be doing some further updates to the method, but states have been starting to ask facilities to use it in their permitting. And we'll probably see that increasingly so as states become more interested in, implementing the regulations that they're currently proposing. So what we have found in our research looking at 1633 is that laboratories are not consistent in the way that they implement it. They are used to taking sort of cleaner samples than maybe is associated with pulp and paper wastewater. And what I mean by cleaner is not necessarily that we have contaminants that are a problem, but we often have color that's associated with our wastewater. And this method can be very sensitive to solids content. So some of the labs will look at a sample and it'll be, heavy in color, and they'll say, oh, that's solids contamination, we need to dilute it. And what that does is it raises your reporting limits so that you can't necessarily be compliant with either the project needs, or if it's a regulatory request, what the regulatory request needs are. And so that can throw your sampling program off. So one of the things we've learned is it's very important to have a discussion with a laboratory beforehand to have them understand what the solids content of your samples is going to be. If it has a lot of color, make sure you distinguish between color and solids, that they're not the same thing and they don't interfere in the same way. And the laboratory should understand that if you have a reporting limit you're trying to achieve, they need to be very selective about the way they dilute those samples to ensure that they'll maintain the robustness of the method to achieve that reporting limit. These are about $400 to $550 a sample. One thing to note is, like I said, historical data has been collected with 537.M. So 1633 not only analyzes different analytes than 537M, but it also will achieve lower limits of detection. So if you didn't find things in your 537M sampling, you may end up finding them in 1633. So you have to consider that when you're designing your next sample run, that you should have some understanding that you may not get consistent results with your historical sampling using a different method. And as we said, field breaks are essential in this type of sampling as it can be complicated and contamination is easy to occur. So with my remaining time here, I want to talk a little bit about testing and products. Testing and products is a substantially different animal in PFAS. Most of the sampling you're doing for like a paper product, you're trying to look at a threshold for what state regulations are calling intentional addition of PFAS versus unintentional addition of PFAS. Most state regulations are geared towards trying to eliminate intentional addition of PFAS. And most of the methods that they are using are a total fluorine or a total organic fluorine method that looks at a threshold. If you say over the threshold, it looks like it's probably intentionally added PFAS. If it's under the threshold, we can say that it's not. And typically that threshold has been about 100 parts per million. But for some regulatory proposals, we've seen it go down to 20 parts per million and even as low as 10 parts per million. There was a proposed limit in California for feminine hygiene products that they wanted to test at a 10 parts per million level. So that will cause some issues depending on what method you're going to use. I have several methods listed here. The most important method here is the combustion class of methods. Most of these other methods are research methods. They're not commercially available. They're only available by academic researchers, and they have some interesting limitations that don't make them really appropriate for regulatory testing. What's important to understand about combustion methods is that following combustion, typically you're trying to measure the hydrogen fluoride content either by combustion ion chromatography or by an electrode probe or some other type of fluorine probe. The fluorine probes are much less sensitive than the ion chromatography is. So those two approaches to a combustion method won't be necessarily compatible. And you're likely to get much more sensitive, a sensitive assessment through a chromatography than you will with a probe. And to meet some sorts of regulatory compliance issue needs, then you may have to opt for the chromatography to ensure you're meeting those sensitivity limits. A lot of state regulations use total fluorine methods sort of interchangeably, but they are different and they have specific uses. A total fluorine method is going to look for all the fluorine content, obviously, in the substrate. Total organic fluorine seeks to take a total fluorine measurement, subtract out the elemental fluorine component, and then you're left with a total organic fluorine product. And the reason we're interested in that is because PFAS obviously are a carbon fluorine type of molecule. So the organic fluorine is what we're really interested in when we're trying to estimate, organic or PFAS levels in a product. The extractable organic fluorine component will be what you can extract out of that substrate. And so this will be potentially what could leach into, like, say, food contact material that's going to potentially leach into food, or some other type of leaching that you're interested in, not just what's totally in the product itself. And then this is compared at the very bottom with targeted methods, like are more consistent with what we see in the environmental space of looking at individual PFAS. And we'll talk a little bit about the differences in comparing these various types of methods. So again, contamination is something that is a common problem. We always want to use we always want to use blanks when taking these. We always want to obtain PFAS-free equipment from a laboratory that we're working with. And we want to have a discussion with the laboratory about what types of limits we're trying to reach and what equipment is necessary to test for these very specific types of total fluorine methods that might be available. So there's specific guidance for how you mesh your paper product. We're typically looking for 4 to 5 grams of sample. We're going to place these in PFAS-free zip top bags and seal them and ship them to the lab. When sampling for products, oftentimes products are not just paperboard, right? There are things that are applied to it. If we're talking about inks, if we're talking about coatings, if we're talking about anything that's being applied to the paperboard, we want to get separate samples of those things and test them individually so we can determine if PFAS is showing up or if total fluorine is showing up, where that's potentially coming from. Because as we'll see here, there are numerous types of interfering products that are associated with this method. If we're thinking about other halogens like chlorine and bromine, those can be interfering and give you a high bias in your total fluorine. Anything that is mined or coming, from the ground, like clays or talcs, sometimes those can be contaminated with elemental fluorine. And one of the biggest issues we've seen is the methods for subtracting the inorganic fluorine from the total fluorine is not very good at this time. And so we do see a lot of high biasing in a total organic fluorine method because we're not able to get all the inorganic fluorine out of it, and so it overestimates that. Another issue that we talked about before is there are various thresholds that we might be measuring for. Typically 100 parts per million is the threshold that we're targeting for most of the regulatory space for products. But if we go down to the 10 parts per million area, we might need to recalibrate the instruments that are being used for this analysis. So if a laboratory is not aware that this 10 parts per million threshold is what you're seeking to achieve, you can see that if you target a certain concentration in your calibration curve, the error limits at the higher end and the lower end of the curve go way up. So if you're actually trying to look for 10, you might have a very high degree of error at that level for the calibration curve of this instrument if you have calibrated for 100. So it's always important, again, to have a conversation with the lab so that they understand exactly what concentrations you are trying to test against, so that you get data that meets your needs in testing for total fluorines and total organic fluorines. And the last issue I wanted to bring up, this is a chart that shows a correlation from a study that tested both targeted methods and total organic fluorine, or total fluorine rather, in the same study. And what we see is there's virtually no correlation between those two methods. And what this means is you can test for targeted analytes and get hits for PFOS, PFOA, PFHXS, something like that. And your total fluorine will be under the reporting limit, because the reporting limit for the total methods are much, much higher than in the parts per billion, high parts per billion, whereas the reporting limits for the targeted analysis can be in the low parts per trillion. And vice versa, if you have a bunch of elemental fluorine in a sample or things that are not PFAS containing fluorine, you may get a positive total fluorine result and get nothing in your targeted analysis. None of the PFAS actually show up. So when we think about how we use and interpret these methods, it's important to understand their limitations, what they're used for, and that the two don't necessarily correlate to each other. And that's all I have for you. So I'll look forward to questions at the end of the presentation.
Thank you, GIF. Greatly appreciate it. We're now going to transition to Dan Curry of TRC. He has his environmental degree from Rensselaer Polytechnic Institute. He has been active in the forest products industry his entire career and attending TAPI events for 38 years, including leadership roles in the Environmental Committee for over 15 years. For 12 years, he was an environmental engineer supervisor and safety supervisor at several mills in with Champion International. Since 1997, he has been providing environmental compliance and risk management consulting to the industry, except for the 2 years where he was the Director of Environmental Health and Safety for Evergreen Packaging. Recently, Dan has been chairing the North Carolina Manufacturers Alliance Contaminants of Emergence Concern Committee, leading that group and providing comments to the state of North Carolina on the development of PFAS groundwater and surface water standards. And with that, Dan, we will have you share your presentation.
Okay, great. Good morning. I guess we're afternoon now for some folks here. I appreciate the opportunity to be here and speak to this topic. What I'm going to talk about is some of the regulatory issues associated with PFAS. GIF did a good job of kind of teeing up some of the challenges, some of the places it's used. I do want to acknowledge Mark Robinson, also a colleague in my organization here, who has also done a lot of presentations on this. This is a kind of a combined effort there. I do want to make a quick disclaimer on this, is that this is a kind of a reference presentation only. The regulatory issues on PFAS are changing quickly and all the time. And so before you make regulatory interpretations or legal interpretations for legal or capital expense or any other purposes, please make sure you are consulting your own environmental group and your own legal counsel. So kind of a quick overview. I want to talk about kind of the PFOA and PFAS were designated as CERCLA hazardous substances. I want to talk about what that means and kind of what the impacts are of that, also associated with ASTM phase 1 due diligence as we go through acquisitions and other work on the as we go through our business. We want to talk about PFAS liability risk management, talk about the changes that have happened over the last year around EPCRA TRI reporting, and then this upcoming TSCA regulatory reporting rule. Any one of these topics we could do an hour-and-a-half presentation on, so I will be hitting them at a pretty high level, trying to just make people aware of the things that are out there and some of the things that they need to be working on. We could talk about MCLs, we could talk about groundwater standards and surface water standards and potential air standards coming up, all the things that are pending and going on, but there's a lot happening. And so again, I'll be hitting this stuff primarily at a relatively high level. So I think that GIF did a good job talking about PFAS and kind of where it is and kind of what's going on with it. And again, if you look at just a quick conceptual site model, the PFAS it's kind of ubiquitous in the environment and it moves throughout the environment. He talked about air deposition of PFAS, talk about PFAS in products, and then PFAS ends up in wastewater treatment plants, ends up in river. The beauty of the PFAS material is that it doesn't break down. The part of the PFAS material that is a big problem for us is that it doesn't break down. So in the PFAS was designated as a CERCLA hazardous substance, and that occurred earlier this year. And that was the importance of that is that it changes the entire regulatory environment in certain regulations around PFAS. CERCLA, just to real quick, it requires that you report things, but it also drives the Superfund issues and Superfund regulations is what is considered a CERCLA hazardous substance. Up until now, a CERCLA hazardous substance has kind of been in this body of other hazardous type materials from various other regulations. PFOA and PFAS and their salts, which are the only substances that we're talking about when we talk about CERCLA, they don't reside in any of these other, at least not yet, in any of these other rules and regulations. But effective July 8th, they are part of CERCLA. but they are not yet part of some of these others. But there's things going on that may bring it into that. So that's kind of the uniqueness of the PFOA and PFAS being designated as a circular hazardous substance. Basically, EPA determined that they may present substantial danger to the public or to the welfare of the environment, and therefore they felt that EPA designation would result in meaningful health benefits. So they made the designation, and what that does is it allows EPA to deploy the full suite of CERCLA tools to identify, characterize, and clean up contaminated sites expeditiously, and also to go after liability and folks who they believe are responsible for the PFAS contamination, to get money to clean up sites associated with any PFAS or PFOA contamination. The other thing that impacts us, regularly in our operations is release reporting. Certainly, there's a list of chemicals that, like I said, showed earlier, that if you report beyond a certain limit of a particular one of those compounds, a circular limit, then you have to report that release. You have to report that release to the State Emergency Response Commission, to the National Response Center, and now PFAS sits on that list, as well as the opportunity to sample and analyze and potentially have to clean up contaminated sites associated with any kind of a PFAS that becomes identified or recognized in any of your sampling or testing. This can happen during a 5-year regulatory review or consent order negotiations. If there is a potential that PFAS is in a potential contaminated area, you're going to get asked to sample for it. And if it shows up, PFAS or PFOA, at a level above what may be state requirements or the MCLs, which we'll talk about more a little bit later, then chances are you're going to get the opportunity to investigate, delineate, and remediate to levels at those sites. This, I have not heard of this happening yet, but I am quite certain that it is in the future. And of course, that will lead to litigation and cost recovery damages as you look for people who may be liable for the associated PFAS in the groundwater, whether it's you or whether it's a former owner or whether it's somebody off-site. And of course, additional listings to the national priority list of the surplus sites. So going back to the reportable quantities, the reportable quantity is 1 pound per 24-hour period. Now, 1 pound in terms of PFAS is a lot of PFAS in general. And really, again, I want to make sure we talk about it. For this rule, we're talking about PFOA and PFAS, right? So if you're looking at 1 pound, you're talking about 2 to 3 million gallons of a typical of fluorinated AFFF or firefighting foam. And you're talking about a million gallons a day of wastewater at 120,000 nanograms per liter. And again, those are very high numbers. So the likelihood that we're going to have a lot of people running out reporting a reportable quantity of a PFAS release it's pretty unlikely, and it has not proven to be something that is going on. There's not a lot of people reporting that right now. In terms of enforcement action, when EPA issued this ruling around it being a hazardous substance, they also put out an enforcement discretion memo. Basically, they're saying we are not looking for innocent parties around PFAS releases. In other words, POTWs and community water utilities, they bring it in and they discharge it, right? And that they are considered innocent parties. Municipal systems that have stormwater systems that are included, POTWs or solid waste landfills, farms that are applying biosolids that are receiving PFAS in the biosolids from someplace else. Basically what they're saying is we're not really interested in those innocent bystanders, if you will, in this PFAS issue, but they are looking to target manufacturers, federal facilities, much to the degree that Giff talked about in terms of places where you have firefighting foam practice areas, or many Air Force bases and military bases that have used firefighting foams, and then other industrial sources where there may be PFAS. But they're looking for the entities who significantly contribute to the release of PFAS contamination, and they will pull them into, as I said, these PRP, this potential responsible party settlements, and then and settlements with EPA around that can possibly provide some protection from third party claims, which is just another consideration. So again, we talked about Superfund. If you have a Superfund site, or if you have any remediation site, the 5-year reviews or consent decrees or administrative order on consent, they could pull you into them now saying, well, PFOA and PFAS are now considered hazardous hazardous constituents, and now we want you to sample for them on your remediation site, and then they show up, and now you have a whole new constituent of concern that you have the opportunity to look at. If you are requested to sample, I mean, Giff just talked about kind of the whole issues around establishing sampling objectives. What are you looking for? How are you going to sample? How are you going to analyze? What are you going to look for? And then testing for the PFAS that are regulated within that state. That you really want to focus it as best you can. You want to consider a risk-based approach to the degree that may be offered. And when we're talking about that, then you need to talk, what we're talking about is understanding what are the potential receptors in the exposure pathways. So if there's no way that this potential groundwater is going to be exposed to anybody or anything, and it's not going to be used for drinking water, and you can show all that, then you want to try to get into a risk-based approach early on and limit your sampling to the best you can. And I don't have to go back over the discussion around quality control and sampling and analysis. Giff covered that extremely well. One of the other significant issues associated with this being with this coming up with a hazardous substance designation is that it now falls also into what is considered an ASTM potentially recognized environmental condition when you're doing an ASTM phase 1 for a property transfer, whether you're on the seller side or whether you're on the buyer side. You are, there will be very specific questions asked around PFAS as a result of it being designated. And we've already talked about different areas where PFAS can be found, but I can pretty much assure you any transaction associated with a pulp and paper facility, the questions are going to be asked around PFAS, whether it has to do with your firefighting systems or your fire suppression systems or your coatings or other potential inadvertent uses of materials that could have PFAS in it. And as a result, you could end up with PFAS or PFOA being identified as a recognized environmental condition in your phase 1 report. Releases of PFAS that are other PFAS, if they're regulated within the state, then they could also be considered a recognized environmental condition. And if they don't, if it's other PFAS other than PFOA and other PFAS rather than PFOA and PFAS, they could easily be considered a business environmental risk because of pending future regulations around those other chemicals that just haven't been designated yet. So your phase 1 report could easily have these in your findings and conclusions, whether it's, like I said, whether it's a buyer side phase 1 or a seller side phase 1, and that could lead to additional requests for maybe a phase 2, additional information being requested around what is the potential liability associated with this, and it can definitely impact considerations on property transfers. as this information is going to become part of the deal, right? Part of the understanding of the environmental conditions and environmental liabilities of any kind of property transfer. I would also add to this that this can also impact potential insurance, environmental insurance liabilities, and it could also impact, in some cases, maybe even financing. So these PFAS issues are creeping into basically every aspect of our operations. So obviously, having a good attorney and a good PFAS expert on board as you're going through those discussions is real important, and understanding kind of what the sampling is before either you go sample or you allow somebody else to go sample on your property. So basically, some of the questions you would ask, has PFAS ever been manufactured on site now or previously? And that's not generally the business that Pulp and Paper is in. So that's not what I'm going to spend a lot of time talking about, but certainly prior used or in current operations or firefighting foam or firefighting training areas. If you're nearby a facility that also may have used that and could have contaminated your property, wastewater discharges, and we can talk for a long time about requirements to sample wastewater, which are coming out in state by state as we move along. And then what happens with your biosolids from your wastewater. Those are all very pertinent questions that you could expect to get from somebody doing a phase 1 on a property. So that's kind of the CERCLA piece. I want to talk a little bit now about some of the regulatory updates around reporting rules. And the first one I want to talk about is this TSCA 8A7 reporting, which is basically a reporting that manufacturers and importers of PFAS have to report their PFAS activities basically for the last 12 years, from January of 2011 through December of 2022. This was promulgated under the 2022 National Defense Authorization Act. And this is a very involved reporting requirement. The reporting includes, the chemical identities and structures, the production, the use of the products, use of any byproducts that may be developed, exposure, disposal, health and environmental effects. And this reporting is due, it's like your CDX reporting or your other TSCA reporting that you do every 4 years. This one is now due on January 1st, 2026, and that's a new date that has recently changed. So I want to talk a little bit about this. This is kind of broken into 2 different sections. There's kind of a due diligence time, and then they're going to open up the CDX portal where you actually do your reporting. And you can see these dates have changed because originally the portal was supposed to open actually yesterday, but they knew they weren't going to make it. The portal wasn't ready. And so that's already been pushed out 6 months. So the final reporting date has been moved out 6 months. So we're actually almost in the middle of this due diligence period that we have to get your information and figure it out. 12 years of data is not easy to kind of come by. So some of the things associated with this is it's kind of different from many other reporting that we've done, even for TSCA. But they will use a very similar reporting database, and they'll use the CDR reporting format in CDX. But there's no de minimis threshold for PFAS. So it's not as though if you had a substance that only had less than 1% or less than 0.1%, there's no de minimis threshold. There's no specific list of chemicals, although there is a list that includes most chemicals that would affect most of us. The definition of PFAS is a structural definition. There's some exceptions in the rule, but they're not many. Again, it's a 12-year look back. And with other TSCA reporting, polymers are exempt. Fluoropolymers are not exempt in this rule. So what do you have to report?
Dan, real quick, we've got about 2 minutes left for your section.
2 minutes, okay. So I'm going to get through then this TSCA reporting, and I'll probably leave the other information will be in there. People can look at it. So what you have to report what is known and reasonably ascertainable, and that's information in people's control or that a reasonable person similarly situated might be expected to possess or control or know. So if you're going to say that it's not known or reasonably ascertainable, you want to make sure that's defensible. So there is an opportunity to use generic names for certain PFAS if you're reporting in certain situations, and you want to be able to do that. So again, it just takes a lot of research, and this is probably one of the most important slides that is in here. There's basically 5 buckets that people would have to report under. One is if you're a domestic manufacturer, and we're not going to have a lot of those. The other is an R&D manufacturer. We're not going to have a lot of those. But if you manufacture using domestic or imported PFAS in a reaction, in other words, you have PFAS that you're using and you generate a new PFAS in a reaction, that's a potential, not a high potential within pulp and paper. But imported PFAS chemicals for processing and imported articles are places where we could have potential PFAS implications in our pulp and paper mills. If you're bringing in PFAS articles, and this, one of the things that people don't think about is if you're buying equipment, pulp and paper equipment, whether it's a winder or a some other piece of equipment on the pulp mill side, that equipment could contain substances that have PFAS, articles that contain PFAS. And those things would need to be reported. And again, it's a 12-year look back. And then again, if you're using any kind of imported chemicals that could be required, then you have to report those chemicals as well. Byproducts, as I said, there's not a lot there. On this slide, the big takeaway here is there is a 138-page frequently asked questions document that I highly recommend that you at least scan through, so you have the ability to identify what some of the important issues are. Here's the website is located here. It's real important that your data that you submit be consistent with other places where you're submitting data, your TRI, your CDR, and this one here, this ACE, which is basically your custom import environment records. Those are records that if you have things that are being imported, you need to know what is being recorded here, and that could be being handled by your procurement department. It may be something that you've never even looked at before. But the de minimis, the removal of a de minimis threshold it opens up the fact that your suppliers now no longer have a de minimis in terms of what they need to put on an SDS for PFAS. So as of your first shipment in 2024, a new SDS, if there's PFAS in there, because up until now, you've been exempt if you're under 1% or 0.1% for a carcinogen, that exemption has gone away. So having a system where you are reviewing the chemicals that are coming into your mill or your operations that looks at those constituents because they no longer have an exemption. And that's really what this is about here. This whole section is about. I got a whole section on it, but that is the important thing is that there's no longer an exemption for below 1%, which means that you now could have SDSs in your organization from this year that are showing PFAS in those compounds, and that can help drive some of your issues here. The one thing I would say around the TSCA reporting, there's a lot of due diligence that you want to do around that, and you want to be able to build a very defensible argument for what it is that you're going to put in there. So So take your time and take the time that's available to do the due diligence before the portal opens. There's a lot of legwork to be done. So just a couple of, and this whole slide deck will be available to you, and there's additional information in there, and there's just more, we could talk about any of it,
Great.
that, you know, that goes on and on. But every state is, they're all looking at surface water regulations and groundwater and stormwater and even some air permits. And I'm not even gonna touch on what happened last Tuesday in the election and how that could impact this, but stay tuned. I would say just keep your ear to the ground, because that could impact changes as well.
All
Okay,
right.
and with that, I'm gonna stop sharing and let Heather move us on.
Thank you, Dan. This topic is just so big for each one of our presenters. We now have Dr. Charlie Liu. He's the National PFAS lead. And at the Applied Research Group at Kennedy Jenks Consultants. He obtained his BS degree in chemical engineering from the University of California, San Diego, and his MS and PhD in environmental engineering at the Colorado School of Mines. He specializes in PFAS treatment and has published and co-authored several papers and conference presentations on PFAS treatment. And he is also very well versed in advanced treatment technologies, treatment of emerging contaminants, general water quality, and water reuse. The next 20 minutes are yours, Charlie. Thank you so much for joining.
Thank you, Heather. All right, great. Thank you all very much for attending this seminar. We know we got a little bit of time left, so thank you for hanging in there with me. So in this presentation, we'll be talking more about the treatment of PFAS. So focusing on treatment, the different challenges with water quality, and some costs associated with treatment. So before we begin, I do want to caveat, this is a research project that both Cassie and KJ have been working on for a couple months now. And again, the goal of that research project, as you might have guessed, is to provide a sort of high-level understanding of how treatment might be done in pulp and paper wastewater effluents. And as we all probably know, as of right now, there's really no sort of regulations associated with PFAS in discharge permits, in pulp and paper wastewater discharge permits, but we need to understand what treatment might look like and prepare for that potential scenario in the future. And so that's why we're engaging in this research project. So as I sort of alluded before, and as our presenters before me also mentioned, the concerns with PFAS in pulp and paper wastewater are that, while PFAS have been used in previous pulp and paper products, legacy PFAS may still be present, even though PFAS have been phased out of those products now. And not only that, but PFAS could also be present in the water that's coming into different mills for different unit processes to make those pulp and paper products, right? So PFAS are sort of ubiquitous. They're found in all different water resources, drinking waters, groundwater, surface waters, wastewaters, and even in places you wouldn't expect them to be found. There's research showing that you found that folks have found PFAS in the Arctic, for instance. And again, the concern here is for potential discharge regulations for PFAS coming down the line, potentially. And so the goal of this research project is for us to take a look at some different PFAS treatment approaches that can range from different PFAS targeted approaches like granular activated carbon or anion exchange resins, and also looking at different pre-treatment technologies. So essentially a spoiler for the rest of this presentation are that PFAS themselves are not very difficult to remove. However, it is more challenging to remove PFAS when it is in a pulp and paper wastewater effluent. It's sort of in the soup of other different constituents that we need to have pre-treatment technologies to remove before we can more efficiently and more effectively remove PFAS in that effluent itself. And number two, we want to provide some very high-level estimated costs, again, not specific to any facility, but to at least give you sort of an idea of sort of, hey, what would costs look like per MGD on a conservative sense? So when it comes to PFAS separation technologies, the EPA has designated 3 best available technologies for PFAS treatment. These include granular activated carbon, or GAC, anion exchange resins, or IX, reverse osmosis membranes, and sometimes you might also hear of nanofiltration membranes sort of lumped into here as well. If you don't speak membrane, nanofiltration membranes are very similar to RO membranes, essentially just a very loose reverse osmosis membrane. So again, these 3 technologies were recommended as EPA by the EPA for best available technologies. Now, I do also want to mention that there's also foam fractionation as a technology that is also increasingly used for complex water matrices as a separation technology. So again, the caveat here are that these are separation technologies. They're really the technologies that can remove PFAS from one phase to the other, but don't actually destroy PFAS. And throughout this presentation, we'll really be focusing on GAC, ion exchange, reverse osmosis, and the potential challenges when it comes to water quality with these different technologies. Now, I do want to briefly provide a overview of different PFAS destruction technologies. As you know, if you've been to conferences where they talk about PFAS, this is sort of the all the hype that's happening right now. So when it comes to PFAS destruction technologies, there are many destruction technologies out there being introduced in academia, in research, and also in startup companies that are implementing pilot scale tests and increasingly starting to think more about full scale applications of PFAS destruction technologies. I'm highlighting just a couple of the popular technologies that you might have heard of. The first one is sort of these high temperature, high pressure technologies, such as supercritical water oxidation, or SQO, hydrothermal alkaline treatment, or HALT. When we talk about high temperature, high pressure, we're generally talking about maybe 350 to 600 degrees Celsius. Pressures, you're talking about maybe 3000 PSI. So as you can imagine, implementing treatments for these high temperature, high pressure technologies is very expensive and also difficult because of these high temperature, high pressures. But they are effective at destroying PFAS, and oftentimes they can do it in a pretty fast time as well, a couple of seconds oftentimes for treatment. Now, we also have another different sort of category of treatment technologies, and these are sort of our ambient oxidation and reduction technologies. These are sort of reductive defluorination or electrochemical oxidation, and these technologies have also been shown effective for PFAS treatment. Now, it's important to note that these technologies here, while they're operated at ambient conditions, do take a little bit longer to effectively destroy PFAS, maybe on the order of hours of treatment. Now, it's great that we have PFAS destruction technologies. However, really, PFAS have been around for a long time and are recalcitrant for a reason, right? That carbon-fluorine bond is extremely strong and extremely difficult to destroy. So a couple of caveats when it comes to destruction, right? It's incredibly energy intensive. There are studies showing that it can be maybe an order of magnitude or 2 order of magnitude higher in energy cost than seawater desalination, for instance, to destroy PFAS, right? And so that, again, driving home the point that this is a very energy intensive process. Not only that, but it's not seen as a replacement oftentimes for traditional separation technologies like GAC or ion exchange or even reverse osmosis. And that's oftentimes because we need a more concentrated stream for more effective destruction of PFAS, right? Again, these are very energy intensive processes. And if you have a more concentrated stream, it just provides greater efficiency and more destruction mass at a higher concentration. So that was a brief overview of the different treatment technologies. In the next couple of slides here, we want to talk a little bit about pulp and paper PFAS detections in the wastewater effluent. Now, this here is some publicly available data that was provided from 5 different mills, including recycle and also craft mills. Now, you'll notice that we only have data for 4 different mills shown up in these tables here, and that's because one of the craft mills that we got data for has PFAS detected in the pulp and paper wastewater effluent. However, those concentrations were actually very similar to the concentrations in the feed water of that mill as well. So we assume that essentially that mill had no sort of PFAS present in its legacy processes or in the wastewater effluent. So we didn't include any of that data in these tables here. But overall, this table shows just there's a wide range of different PFAS detected in pulp and paper wastewater effluents, and that's actually largely consistent with what you would see in the environments for different drinking waters, for different wastewaters as well. You often see a combination of different PFAS being detected together. Now, I do want to highlight some of the most notorious PFAS that you likely heard about, PFOA and PFOS, for instance. The concentrations here are actually surprisingly not very high. They're about 20 nanograms per liter, which is actually very consistent with what you would see in a municipal drinking water sense. A lot of groundwaters or surface waters, we're oftentimes talking about each individual constituent is oftentimes less than 100 nanograms per liter. Now, of course, that story would likely change if there's influence of AFFFs, for instance. That's the firefighting foams that Gift talked about at the beginning of this seminar here. Those oftentimes contain micrograms or even milligram per liter concentrations of PFAS, and oftentimes you'll see higher concentrations of those in any sort of waters that are influenced by AFFFs. So again, caveat that this is by no means representative of the entire industry, but this provides us with some good data of what wastewater effluent might look like coming out of a pulp and paper mill. Now, PFAS themselves, again, are not very difficult to remove, but the challenging part, of course, is the soup of other water quality constituents that will impact PFAS treatment. And so this is a very busy table, and we'll go through each of the different constituents together and sort of discuss what the impacts of these different constituents are when it comes to PFAS treatment. And we'll do a little bit of a deeper dive in the following slides too. So the first slide here focuses on TOC and color. Now, do note that there's really no research looking at color for PFAS treatments or the impact of color on PFAS treatment. And so this is an area that needs some more research. But here we're roughly correlating color with TOC concentration. And we see here, on average, the TOC concentrations are roughly 90 milligrams per liter. These concentrations are relatively high when it comes to PFAS treatment, especially from a municipal side, for instance. On the municipal side, oftentimes you see maybe 0.5 milligram per liter or even 2 milligrams per liter at most for surface waters for PFAS treatments. And even when you start pushing it higher, then we end up seeing that there is an increasing impact of sort of this competitive absorption or competitive treatment when it comes to high TOC waters for PFAS treatment. And again, I'll show some data sort of driving that point home. Next, we're taking a look at metals, which includes iron and manganese. These concentrations are relatively high, especially manganese at 0.3 milligrams per liter. These can foul your absorbent media or your high pressure membranes. So also a concern for us to remove before we get to PFAS treatment. Anions, including chloride, nitrate, and sulfate, these can compete with the adsorption sites, especially for ion exchange resins when it comes to PFAS treatment. So again, different constituents to also consider for removal, or maybe just to consider when selecting PFAS treatment alternatives. And finally, cations like magnesium, and there's also some cations that we're missing in this data set, could be sodium or calcium, for instance, that kind of close that ion balance. But magnesium, sodium, and calcium can sort of have an adverse impact of PFAS treatment, especially for the high pressure membrane. So another consideration to think about when potentially implementing PFAS treatment. So that was sort of an overview of the different water quality technology, of the water quality constituents that could impact treatment. That's sort of giving us a brief overlook. And then in these next couple of slides, we'll be focusing more on adsorbent technologies and also reverse osmosis, and sort of diving deep into each of the different constituents that would adversely impact PFAS treatments. So again, as you can sort of start to gather here, and PFAS themselves are not very difficult to remove. We have these technologies to remove them, but the water quality that the water quality constituents that the PFAS are also in this giant soup of, with TOC, with metals, anions, cations, all of these different constituents can have an adverse impact on PFAS treatment itself. So increasingly, we're starting to see that we need to implement some sort of pre-treatment technology before we actually get to implementing PFAS treatment. So we need pre-treatment to remove a lot of the water quality constituents, and then we end up with actually implementing our sort of polishing steps for PFAS treatment. So here we're focusing on our different adsorbent technologies, GAC and ion exchange. When it comes to PFAS treatment nationwide and around the world, generally we're talking about GAC and ion exchange are more widely implemented for PFAS treatment, especially on the municipal side. It's because these are relatively easy to implement. We can buy adsorption vessels, we can design rectangular adsorption bases, and essentially just put this adsorbent media in for PFAS treatment. Right? There's a couple of photos of adsorbent media vessels that have been used for groundwater treatment and also industrial drinking water treatment, industrial drinking water treatment as well. So these are really our more popular technologies that have been widely implemented for treatment. However, the major challenge here is that most of the data currently generated is really focused on non-complex water matrices, right? And these are low TOC waters, low sulfate waters, for instance, right? And so we need to generate more data on treatment of PFAS for more complex water matrices. And with that being said, that also drives home the point that we need to implement pre-treatment before we implement PFAS treatment. And that's because there's just so much competition happening, and that would sort of increase a lot of treatment costs. So in these couple slides here, we'll be focusing on, here we're looking on a TOC for PFAS treatment, right? And so this is some available data based on research papers demonstrating the impact of TOC on reducing absorption capacity of PFAS. On the x-axis, we have total organic carbon concentrations ranging from 0 to 30 milligrams per liter. And on the very right-hand side here, we see the pulp and paper wastewater TOC average concentration is at 90 milligrams per liter. Now, on the y-axis, we have bed volumes breakthrough, essentially just a representation of how well this treatment media works for removing PFAS. Right? And so as we can see here, as we start to increase past even 5 milligrams per liter of TOC, we start to see there's a dramatic decrease in treatment bed volumes, right? The treatment capacity of PFAS for a wide range of different PFAS compounds that are shown on this graph here. So this, again, drives home the point that even at 90 milligrams per liter, these high concentrations, there's a possibility that media would need to be changed out almost every single day, right? And so again, that drives home the point that we need to implement pre-treatment for TOC before actually implementing PFAS treatment. Similar story for ion exchange, although just a little bit better. For ion exchange, we see the same graph here we see a range of different TOC concentrations and the bed volumes of breakthrough on the y-axis. As we get past maybe 2 or 5 or even 10 milligrams per liter, again, we see sort of this dramatic drop-off of absorption capacity when it comes to ion exchange, right? So again, driving home the need for pre-treatment for TOC before we actually get to GAC or ion exchange used for PFAS treatment. Now, there are many different TOC treatment technologies out there, and each mill's wastewater effluent is unique, right? And so each mill would have to do their own evaluation to take a look at, hey, which technologies work the best, and likely have to implement some sort of pilot testing or bench scale testing, at least to understand which combination of technologies might work the best before we actually get to PFAS treatment. Now, focusing on ion exchange, right? So we just talked about TOC, the impact of TOC on treatment of PFAS by GAC ion exchange. Now we want to look at impact of different ions on PFAS treatment. So here we're looking at the impact of sulfate for PFAS treatment for ion exchange. Sulfate doesn't really impact PFAS treatment by GAC, but more so for ion exchange. So here we have a graph here demonstrating that here's our recycled and craft sulfate average concentrations at maybe 250 to 400 milligrams per liter. Here in this data, we see that as we increase in sulfate concentration, we see a rough correlation with the decrease in absorption capacity for PFAS by ion exchange. Again, very rough correlation, but there, again, isn't too much data out there for PFAS, for the impact of sulfate on ion exchange treatment. But we do see a rough correlation, and a lot of vendors will oftentimes cite sulfate as a clear constituent that will decrease the absorption capacity of PFAS by ion exchange. So there are many different ion pretreatment technologies. Sulfate has ion exchange, lime softening, or even biological treatment, for instance. Again, each facility has unique wastewater qualities. So different pretreatment technologies or even the combination of treatment technologies would need to be piloted or even evaluated at the bench scale for more effective treatment. Taking a look at iron and manganese, again, this here demonstrates, we see a picture on the right-hand side here that's showing the impact of manganese on adsorbent media. On the right-hand side, you'll see this picture of ion exchange resins that are essentially yellow and white at the beginning, but over a couple of months of operation, we see that this particular pilot study had high concentrations of manganese in the groundwater, and that ended up fouling our resins. And sort of essentially just ruin them, and no absorption was happening anymore. So again, iron and manganese are critical constituents that need to be removed by maybe prefiltration or oxidation, again, in combination with treatment train that is needed for treatment, or that a treatment train that is needed for pre-treatment. Now, coming down to looking at PFAS treatment, sort of the estimated cost associated with PFAS treatment for GAC and ion exchange. So here, I'm only showing, again, very high level capital costs. Again, caveating that this is very non-mill specific. This is just a high level estimated cost. So generally what we oftentimes see in the industry is about $1 million per MGD for only GAC and ion exchange treatment. So that includes only capital costs, right? And so this is implemented treatment vessel. And oftentimes as we go up in MGD, in MGDs or flow rates, oftentimes we do see some economies of scale. So the treatment cost there would decrease, maybe about 500,000 per MGD for treatment costs, but again, very expensive. And again, this is only capital costs, right? So we do also have operational and maintenance costs, or O&M costs, that we need to change out media for as well. So that's sort of, as you can probably think, this is sort of that balance between implementing a adequate pre-treatment, right, versus how frequently you want to change out your media. If you have the best pre-treatment in the world, then your media might not be changed out as frequently, but implementing that pre-treatment might be very expensive. Right, so it's sort of that balance between implementing enough pre-treatment and how frequently the media is being changed out for O&M costs. And so O&M costs generally we're estimating maybe $500,000 to $750,000 per MGD for annual costs for both GAC and ion exchange. Now the caveat here is that we're assuming about 2 milligrams per liter of TOC, and we do again need to balance that pre-treatment with media change-out frequency. And here we are also not including any pre-treatment costs, right? So as you're probably gathering, right, cost of PFAS treatment is going to be very expensive, especially if any sort of regulations come down, right? And so we need to implement some sort of pre-treatment cost before PFAS treatment is actually implemented for GAC and ion exchange. Now, in the last couple of minutes here, I do want to show just some data for treatment by reverse osmosis. This is just some data here demonstrating that we do have effective rejection of PFAS by reverse osmosis membranes. We generally see about 99% rejection of a wide range of different PFAS by these high pressure membranes. Now, RO membranes really aren't used for PFAS treatment, and oftentimes they're really only used in instances where a facility might be thinking about reuse, right? And so RO membranes, if you've used them before, we know that they are very, very susceptible to fouling and very sensitive to water quality. So that means we do need quite a bit of pre-treatment for RO, and oftentimes low pressure membranes like MF or UF membranes, microfiltration or ultrafiltration membranes are used prior to RO membranes. We also have a wide range of other different technologies that are oftentimes used as pre-treatment for RO membranes. But again, the challenge here is that RO membranes, again, they don't remove PFAS, right? They only separate PFAS. So we are still left with that concentrate stream or that brine stream you might have heard about before, which still contains a high concentration of PFAS, right? And so the challenges here is that we still would need to remove the PFAS in that concentrate stream. And it not only contains higher concentrations of TOC, but also higher concentrations of salts and also higher concentrations of PFAS. So, and more challenges with high pressure membranes. So that's why a lot of folks are starting to think about high pressure membranes in combination with potentially destruction technologies. Now, as you can imagine, treatment costs for RO are likely higher than GAC ion exchange. We're talking about roughly maybe 4 million per MGD, likely lower. There's a lot more economies of scale when we talk about RO and NF or RO membranes, and also sort of low pressure membranes as well, about 2 million per MGD for UF. Again, these are estimates that are incredibly conservative. We want to make sure that we sort of have a rough understanding, the order of magnitude of cost associated with treatment per MGD. Now, OM costs were roughly assuming about $1 million per year, and that's because of all the chemicals that are needed for treatment for RO and UF membranes. And finally, as I mentioned before, right, the concentrate stream still contains that PFAS. Unlike with adsorbents, we have PFAS sticking onto adsorbents. With high pressure membranes, we essentially separate it out from one stream into two different streams. You have a clean water stream, then you have a dirty water stream. And that dirty water stream, we need to also treat for PFAS as well. So more challenges associated with these high pressure membranes.
Okay,
Right,
Charlie,
and then in my last slide here,
we're gonna have to close out pretty quick.
Yep. Just the last slide here is just talking very briefly about foam fractionation. Foam fractionation, a great technology for very challenging water matrices, oftentimes used for landfill leachates, right? And here we're just, this here is just a graph showing that it's very effective for long chain compounds. You can see as we increase in compound chain length, we get about maybe 90% removal to 100% removal efficiency. But we do see sort of this exponential decrease in efficacy for treatment for the shorter chain compounds. So again, promising technology, but for primarily long chain compounds and especially for complex water matrices too. And so to sum everything up here, right, we essentially PFAS treatment again themselves are not very difficult to remove. The major challenges comes into the complex water matrix that we have a lot of competing constituents, TLC, sulfate, manganese, and iron that need pretreatment technologies. And so if PFAS treatment were to be implemented in a pulp and paper wastewater effluent scenario, we would need to implement some sort of pretreatment technology to help knock down these different competing constituents before we actually get to PFAS treatment. With that, thank you very much for your time. And I know we have a couple minutes left for a Q&A, so I hand it over to our moderators.
Thank you, Charlie. Yep, we've only got a couple minutes left. Let me just share this real quick. In case you have interest in the group itself, we wanted you to have an opportunity to volunteer. Scan the QR code and you can connect with Lisa about that. Also, just real quick, in the chat, there was the question that says, if we select separation technology